Hello and welcome back to the classroom. I'm Mr. Wong. We're going through Module 3, Inquiry Question 3 as well, sound waves, and we're going to look at how the relationship between distance and intensity of sound changes as you go closer and further away from the source. Now this is following on from the lessons that we talked about with different sound waves and standing waves, how that's generated different harmonics. So if you haven't watched that video, I would suggest you to watch that first. Anyhow, let's get started. So what you can see with the sound, even with the sound source here with this diagram, is whenever we generate sound, sound is a wave. Okay? Imagine you were in a pond and you drop a pedal in that pond. The waves will ripple. Now, in which ways does the wave ripple? It ripples in all directions. So sound is the same thing. When you generate a sound from an audio, a headphone, headset, a speaker, that sound travels in all directions. So what we could say is it's expanding like a circle. Now we know what the area of the circle is. We know that circle is 4 pi r squared. So we're saying the area that's being covered by the sound wave is the same as the circle moving progressively further and further away. Okay? To give you a bit of context, the intensity of sound we know from a single source can be related in this particular way. So imagine we're looking at the energy generated from the source, the actual energy or the actual power that's being generated from that light source or sound source. That's going to dictate your intensity, but also how far away you are from the actual device. So if your speaker is here and you're standing here, okay, you're going to hear a much higher volume or much higher intensity of sound. Remember, intensity and volume, same thing. Then if you were standing further away, the volume would go down, the intensity of the sound would also go down. Now obviously you can't change the source of the sound, so you can't change the energy that's being released or the kind of sound you're generating. So if we imagine that P is a constant value, we can just equate it to 1, and we find that the intensity of sound, okay, is inversely proportional to the square of how far away you are from it. So if I am 1 meter away from it, okay, 1 meter, and then I am 2 meters away from it, this formula states that I will have actually heard a quarter of the original intensity of sound that I hear here, if I go just increasing my distance by 2. Or going to 2 there, okay? This formula, we will come back to it again in Module 7 when we actually talk about the intensity and the power generated by sun, but this is true for light as well, okay? So keep that in mind. Now, a different thing we can come through here is the intensity of sound if we are moving away from the source, okay? So this formula is just encountering the same thing I talked to you about before. If we have, let's say, our speaker here, and we stand here, and then afterwards we move back a couple of meters there. Obviously, the intensity of sound we hear here will be different to the intensity of sound we hear there. We actually find that there is a nice little ratio that we can work with, and that's given by this formula here, or what we call the inverse square law of intensity. Okay, so that's really nicely done. Alright, our way of measuring the intensity of sound is using decibels. Okay, the threshold is this value here. We don't really need to worry about that, but what you do need to understand is this is a logarithmic scale. So although it says it's 70 decibels and then it's 80 decibels, it's actually not as straightforward as that. So although it's from 70 to 80, what's actually being shown is it's twice the amount. So if I go from 70 to 80, okay, 80 decibels, it's twice the volume of 70. If we go to 90 decibels, that is 4 times as loud as 70 decibels. If we go to 100 decibels, okay, obviously that's even more larger than that as well. So that's about 8 times as large. Okay. If we look at the actual threshold, so the safety net is 58 decibels. That's the range that will ensure that you don't experience any hearing loss. If you go any higher than that, then obviously there will be trouble. So if we have a sporting event, an exposure of 14 minutes is enough to cause permanent hearing loss. If you hear a siren from emergency service vehicles, 1 minute exposure can cause permanent damage there. Okay, the reason why the higher decibels can cause this is it actually breaks down your hair cells inside your ears, and that affects how well you can register sound. One of the examples of people who experience really high volume environments as part of their workplace is a concept called tinnitus. Okay, tinnitus is a temporary hearing loss condition that can affect how well you can register sound, and it's also that weird tingly feeling you hear on the side of your ears where you feel like you blocked off from registering any sound there. So that's kind of the experiences there when we talk about hearing losses under high volumes. Now here's something that's applicable to a lot of people: Sydney trains. Okay, I want to highlight a little particular line. I think it's the T9 or T1 North Shore line from Waverton to Wollstonecraft. Now this is the exact image area that they're in focus here. Now along this strip there is a nice little curve around this railway, and what's actually happening here is as the trains go around there, it causes a massive friction with the tracks, and it causes a really high pitch squeaking sound. Okay, so from that record we find that from Wollstonecraft station the average train sound exceeds 100 decibels. Now remember, the threshold for good hearing or protective hearing is 85. So if you're 85 below, that's great. If you're 85 above, you need to wear some protective gear in terms of protecting your ears. There's about 400 odd trains that go past this station every day, so it's actually a health occupation issue or work health safety issue for residents who live in that particular strip next to the trains. Okay, now let's have a go at calculating some questions with the intensity of sound. So imagine we're at a concert and a speaker at the front of the stage is 1 meter from where you are standing. Of that particular sound you hear is 2 times 10 to the power -2 watts per meter squared. So that's just measuring the power and also the area covered. If you move, this intensity drops. How far have you moved from the stage? Let's sort it out. Okay, so the inverse square formula of intensity of light or sound, sorry, I1 I2 equals R2 over R1, and we're going to also put the square roots in. We're going to put the squares in as well. So we have square of that. We know the original intensity, we know what that is. That's 2 times 10 to the minus 2. We also have 3.2 times 10 to the minus 5. And then we're trying to find R2. R2 is what we're trying to find. The distance of the original is 1. So that. So R squared, or R, get rid of that square. We square root the other side. And that's the overall distance that we would have to be. We'll go through the answers in a second, or write the answers down there. Going through the second one, we have a sound wave, and we can call that I1. And then we add a distance there, that's R1. What would the intensity be if we went to this particular distance? So that's R2 there. Okay, so I1, I2 times, or equals to R2, R1 squared. Okay, so there's a couple of ways you can go about it. You can rearrange to make I2 the subject. What I'm going to do is I'm going to inverse the equation around here. So I'm going to get I2 over I1 over R1 over R2 squared. So that's just following through. You can see I've just flipped both sides around. So I2, the intensity, is R1, 5 meters, divided by R2, 22 meters squared, times 4 times 10 to minus 4. That's the intensity once we've moved from this position 1 here and then back a few meters there. So let's look at, I'll write the answers down. Okay, so the radius that we have here is about 25 meters. And the intensity that we have here is 2.07 times 10 to the minus 5 units watts per meter squared, or you can write it as watts meter to the power negative 2 square as well. Okay, so that gives us an idea of what the intensity of light is. So this is a really short one here, just a quick summary. So what we know about the intensity of sound is that the intensity of sound is inversely proportional to the square of our distance. We also know that the amount of energy passing through, or what we define as intensity of sound, is the energy or the power that's traveling through per square unit, area squared. And we came up with this formula here. Okay, so this is obviously used in measurement of saying if we have an object moving from one position to another, what is the different intensities of sound that we get from there. Right, so hopefully that explains to you what and how the intensity of sound can be affected. Please join in the classroom again for our next few lessons, which are still going to be focused on sound. Next is coming up will be beats and the Doppler effect. But until then, please replay the video if you want to catch up on anything you missed out during the explanation. If not, welcome to the classroom, and I'll see you next time.